Nice. Does that work? Yeah, it works. Hi, everyone. Nice to be here. I made it just barely, but I did. There's no pointer here, right, to click on the slides? Nope. Cool. So yeah, happy to be here and happy to present some things about the Nobel Prize of this year to you. Hope you're as stoked as me. The title I chose was Deconstructing, the 2022 Physics Nobel Prize. But when I was working on this and this presentation, I kind of realized that deconstructing is a bit the wrong way of going about it. Let me just start a timer so I know what I'm doing. It's the wrong way to go about it because it should be an undergraduate talk, and deconstructing means you already know the stuff you're talking about. So we're not going to do deconstruction, we're going to do building up, hopefully. And the goal of my talk here is that you have an overview and some intuition about why these people of this year's Physics Nobel Prize got the Nobel Prize. So this year's laureates are Alain Aspect, John Clauser, and Anton Zeilinger. And they share the prize, each of them gets a third. And they are honored for their experiments with photonic entanglement. So they use light and did experiments on light to prove very foundational things in quantum physics. The honoring from the committee, or the sentence they said why they would honor them, is as follows. So they would honor them for the experiments with entangled photons and establishing the violation of Bell inequalities, and for their general contribution to pioneering quantum information. So we have these three catchphrases in there. First we have, as I said, these entangled photons, so they work with light. And then we have these violation, or just in general, the Bell inequalities, which play a major role, majorly historically, in quantum science and how it was developed in the last 50 years. And then we also have current contribution or actual technology that was built from these kind of things. So I'm trying to tackle each of these three topics by structuring my talk into three chunks. So first, we have kind of characteristics of quantum mechanics that people need to know, or that we have to get an intuition about to understand these kind of things. Then the second part, the weirdness of quantum mechanics, why it doesn't make sense, or why so many people get confused about it, or why we haven't figured it out instantly when we created the framework. And the last part is more of an overview of current developments and what cool things we can do with quantum entanglement and quantum stuff. So I guess one of the most important questions I will be asking today is, does any one of you have a background in quantum mechanics? Seen everything connected to quantum mechanics or have knowledge about it? Raise your hands if you have. Cool. Nice. I'm prepared for this. I'm not sure if you are prepared for this. So we have to get some knowledge about what can happen with quantum, but on a very, very, very basic level. And I will try to make it as intuitive as possible. But if it is not intuitive, then please ask questions rather early than later, because then we can deal with the problems or try to solve them. So what is quantum mechanics? It's a good opener. Quantum mechanics is a physical theory which describes systems and its evolution. So we kind of can explain how the world evolves with quantum mechanics. Now, we cannot apply this to all systems, because else you would already be experts in quantum mechanics if you would encounter it every day. No, we apply it to very small systems. So the systems where we usually encounter quantum is either single particles or ensemble of particles, electromagnetic fields that are very weak, or many-body systems such as superconductivity or conductors in any kind. If you look at electrons in a metal, then this is where these effects come into play. And this is not stuff that we would encounter in the classical world we see around us. So we have a major problem, which is that we don't have a lot of intuition about these kind of things before we study it. So this is kind of my biggest challenge today, and I hope I will do a somewhat acceptable job at it. To get you some intuition on this, because we need some quantum mechanics. So today we will only look at finite dimensional quantum, which is good for you, because I don't know what this exactly means, but it somewhat translates to first bachelor year linear algebra. So we don't need to know more than matrices, vector spaces, and some linear operators, or matrices, I guess, in this case, which is nice for us. But before we get to that point, and I hope this is not the deal breaker, I need to confuse you in some way to establish where quantum mechanics comes into play initially. And I thought for a long time about how I want to present this, and this is the way I came up with it. I'm not sure if it's cool or if it's understandable, but we'll see. So first we're going to try to connect the world we see with quantum mechanics to establish a foundation. So what is quantum? In quantum mechanics, we associate new objects to classical objects we know. And these new objects have almost nothing to do with the objects we know. So it can be super confusing at first. But I just want to make an example to kind of build up this, and then we can forget about it again. But this is needed to see why these people started working on the things they did. So in a classical system, like our moving particle here, we have some mass that can move around. It's described by some location, so we know the position, and some momentum. If you have this, we know every information available about this particle, and we can describe it. So the system for our classical system would be just R3 or R6. I guess there could be an argument made. I think R6 would be better. So we have the position and the momentum. Then we have the observables. This is the measurable quantities that we know of the system, is also the position and the momentum. And then the state of this system could be, is just described by the combination of these two. So if we know these two, we know everything. Quantum mechanics deals with these same quantities, and we have like a correspondence between this classical system and the quantum system that kind of gives us a relation. So I just want to highlight the very fundamental correspondence that is cool for us and that we need to look at all these interesting phenomena. The first is that in quantum mechanics, we don't have any system. We have a Hilbert space. So our system that we look at goes over to a Hilbert space, which is a fancy word for a vector space. So it's just a vector space. We have vectors in there. For our moving particle, it would be some fancy space of functions, but we don't care about this, really. Our observables, so the position and momentum, go over to Hermitian operators, which is a fancy word for our case for a matrix. So we don't have these values anymore, but we have some matrices that describe the same thing that we would see here. Also not really necessary for this case, because this is the most is a very complicated one to do to see the quantum analogy, but a very easy one to see the classical picture. There's somewhat a difficulty because you can't do both at the same time. And the last thing is the state. In quantum mechanics, we describe it by a vector in this vector space. Now, why is this so complicated? I said this is first-year linear algebra. It really doesn't look like first-year linear algebra. This is because it isn't. This vector space is not even finite dimensional. So we did something wrong. Or we didn't, because, as I said, I think this is the most intuitive example to see how we can go from classical to quantum, but it's not the easiest to do stuff with it. The easiest to do stuff with it is if we look at a spin, which is a super non-intuitive thing in the classical world. It doesn't exist. So for this talk here, we will think about the spin as some particle that has, I think the best way to think about it is that it has an actual spin of its own. So it turns either in this direction. This would give you this up arrow because you just look at the angular momentum. If it points up with the right-hand rule, you have a spin around this axis. This you would call the up state. Or the other way around, it spins in the other direction. You have the down state. Physically, it is not this rotation. I just want to make this clear. We don't know what it really is. It's just there, and we can observe two different spins. So why is this cool to look at? It's cool to look at because if we look at these three things that we need to describe our quantum system, we have the Hilbert space, which in this case is just C2, so the complex vector space with two vectors. And the observables, so the thing that we can measure is, we can measure like if this is up or down, so if we turn in one direction or the other, if we have an up or down spin, which is now not a nice value up or down anymore, but a matrix. Just bear for me for one moment. And we have these states, which are not some weird position, momentum, or anything function. It's just the standard vectors of C2. So if you have spin up, we have the first standard basis vector. If you have spin down, we have the second standard basis vector. We can look at it in this way, and it makes complete sense. This is all we need to describe this spin system. And already this little example has super nice conclusions or effects that we can observe. The operator just, bear with me for one moment. It will make a bit more sense when I go a bit more into detail, but just one moment. So what we have from this is we see that now we have our nice first year linear algebra. It's not spooky. The only thing that's spooky is that we really don't know where it comes from. So we can observe this. The spin is something you can really measure in the real world. So you can do an experiment to see it, and it behaves like C2, like a small vector space. And I think that's already pretty cool. So if we have this example of C2, we can already do some cool things with it. First of all, if we push on this analogy between linear algebra and this spin system, we can see that in C2 we have these two basis vectors, and in the spin system we have the same, as I already told you. But this means that these two states kind of give us all information about the system state we need to know. The second thing is that if we have this linear algebra analogy, we can not only look at these two states, but we can make linear combinations of it. So we can take these basis states and do some linear combination with some values, and we can do the exactly same thing, a similar thing in this spin system, where we can do linear combinations of the up and down spin, which now exist at the same time. So we kind of explore a whole new world. We don't need to know if we have an up or down spin at one moment, but we can do linear combinations. This is one of the foundational things that leads to all this interesting stuff. So up there, as you can see, we have these two basis things, and then we can combine them in your combinations. Does that make sense until now, or have I already lost you completely? Kind of cool. Any questions? Nope. Okay. So the first really interesting effect that occurs is that we can have these superpositions or linear combinations. And these describe our spin state completely. So we can use this. This is everything we need. The second, and this is the last thing that I need to build up before we can really look at the work of the Nobel laureates, is we need to look how we can obtain stuff from such a quantum system, so how we can measure quantities. And this is where these matrices we've seen before come into play. And there we need to establish two axioms, I would say. You can look at it how you want. Either you define quantum mechanics with these things, or you define quantum mechanics and then you need the axioms. So the two things that people just postulate, so there's no intuitive reason to kind of understand this or way to deduct it from the classical world. It's really, people have tried, have measured stuff, and it looks like this. We don't know if it really is this, but it seems to agree with everything we can measure. So this is what people say should be true. The first thing is that if you have these operators, this is the things we can measure, then if you do a measurement, you can only obtain the eigenvalues of a matrix. Okay, we can make this connection, seems unreasonable, but we can do that. And the second axiom is that if you measure something, you project the state you have into the eigenstate of the corresponding eigenvalue. So let's look at an example what that means. If we have our neat little spin system and have a superposition of this up and down state, which we can also look at this linear combination from linear algebra, then we can do, for example, a spin z measurement, where I really should have drawn the z-axis here. Z-axis would also be in this direction, so exactly where these two point. And this z measurement is carried out by this operator, this diagonal matrix. So if we measure the spin, as we see from the first axiom, what we really can measure is the eigenvalues of this system. Now, what are the eigenvalues of this system? Anyone? Let's get this interactive. Yes. Yes, it's 1 and minus 1. It's a diagonal matrix, so these are the eigenvalues. And the corresponding eigenvectors are, if you want to find a vector that gives you the same vector back, if you put it in, is just the standard basis vectors. So what it really means is if we measure the z-spin of this state, we can either measure the up or the down spin. So this is a linear combination, but if we measure it, we measure either up or down. So standard basis vector 1, standard basis vector 2. So, and we collapse the state, so we had this one initially, and we put it into one of these. Which one of this it is not a priori known. So you do a measurement and you kind of roll a dice, which Einstein hates. This is one way to look at it. Exactly. So this is the key principle in all the experiments that the Nobel laureates did, is to use these measurements to collapse such a superposition state in some way. Cool. Now, to put it into historical framework, we need one more thing, and this is the Heisenberg uncertainty principle, which is, lucky for me, explainable in an intuitive way. The Heisenberg uncertainty principle says that if you have complementary quantities, whatever that is, then you cannot measure them simultaneously with arbitrary precision or accuracy. So if you have two quantities that are somewhat like related to each other, then you cannot measure them at the same time. The most famous example for this is position and momentum. And we can look at this in this like neat little trick experiment way. If you have a particle and it goes somewhere with some momentum p, and you do nothing, then you know the momentum p of the particle because it didn't do anything. So it just propagates, but it will change its position. Now, if you want to find out where the particle is, remember single particles are very, very small, so you need to find out where it is in some way, use a microscope, use some tweezer, use some slit experiment. Then you need to put in your measurement device, which is marked by these slits, to find the position. But if you do this, your particle can somewhat couple with this device, or it will interact with it, and afterwards you don't know the position anymore. So the position and the momentum in this case are these conjugated variables which you can't know with arbitrary precision at the same time. Either you know the momentum or the position. If you measure the position, you don't know the momentum. If you measure the momentum, you don't know the position anymore. And luckily for us, we have a similar thing in our little spin system. And this is if we measure along different axes of our spins, we cannot know the variables precisely. So if we look at the up or down spin, we don't know the left or right spin anymore. And this is used to establish, or this is a very basic thought that leads to these historical developments that lead to the Nobel Prize. So now it gets interesting. Now if we have this, we can ask ourselves, what happens if you have more than one particle? How does the situation change? And for this, we have a very, again, unfortunately non-intuitive property of quantum systems, which is that they don't behave like classical systems where you have two particles, you just add the description of both of them. So if you have two particles and you know the momentum and the position of both of them, you know everything. So a full state or description of this system, two particles with momentum and position, would be you just know the momentum and position of each of them. This state or this system can always be described in this form, where you have the first particle and then the second particle. There's nothing else. In quantum mechanics, it's a little different because we don't have the direct sum of our two systems, but we have the tensor product, which you also should know from first year linear algebra, which gives us one neat little feature, that is that if we have for two spins and have, for example, up spin in the first one, down spin in the second one, or the other way around, we can also do a different state that is not already described with these two. Namely, we can do linear combinations of these pure tensors of our system. So these two would be pure tensors, and then we can just add them up, which would look like this. So we don't have up or down or up anymore, but we have a linear combination of these two combinations of the system. And this is quantum entanglement. This means that we have something in between and that the system state cannot be explained by just looking at one particle and then the other, as in the classical case. No, it means that really we need to look at the entire system, and there's somewhat more space or more richness in the system than just looking at individual particles. I'll elaborate on that a bit because it's the key component, really, not only of the Nobel Prize, but also of quantum mechanics, in my opinion. And I'll also define it properly for you. So if you want to define entanglement, we need to define the opposite of entanglement, because it's way easier to say what it is. So we first need to define what it means to be separable, which is the opposite of entanglement. We call a quantum state separable if it can be written as a pure tensor. So I'd much rather show it to you the example first. A pure tensor means that we can write our system and describe it with one description that fits to the first particle and then another one that fits to the second one. So we can always reduce it to a pure tensor. That means one state on the left and one state on the right, and not some weird sum. Classical systems are always in a pure tensor form, if you want to think about it in this way, because we can, as we've seen with this two-particle system, always reduce it to, we have momentum for the first particle and position, and then we go over to the second system and say, okay, now we have momentum and position for the second one. Entangled now means that it's not separable, which is not a very neat way to define it if you want to show entanglement experimentally, because you cannot do everything else. You cannot show that everything is separable just to deduct that it's entangled. But what does this mean? How can we phrase this or put it? It's exactly the state that I've shown you before. Is an entangled state where you add these two combinations of up-down or down-up in a linear combination. If we want to really write it in a formal mathematical way, it would look like this, where we have the tensor product. So now we can see whether we've understood the concept on a basic level, because we can try to see if this one is separable. So if we can write it as a pure tensor. So how would we go about this? I think this is a linear Linalc 2 exercise even. Or I think I did that at some point. So if we want to see that, we kind of want to factorize these two components in the same side of this tensor product. So we're trying to see whether we can pull this out or factorize it. But if we want to factorize the left side, then we have a problem, because on the right side here we don't have the same directions and we can't factorize it. So we're really trying to pull something out and factorize it, but it's not possible because we have this complete anti-symmetry. So we can only write it as this, and therefore it's not separable. I understand this needs like some minutes or I guess days or weeks to make a bit more sense of it, but I hope you're getting the basic concept. This can now be neatly applied to one thing. Yeah.
The first example by the separate definition. What do you mean by up, down, and then this bracket? Like, do you mean the first particle has been up and the second particle has been
down? Yes, exactly. Exactly. So this, the left here would mean that the first particle is up and the other particle, the second particle, is down. Okay, yeah. Mm-hmm.
Mathematically? Or just what would this be now?
Okay.
You say this is a state.
Yes.
Right. So this is a state, and the state of the system is that the first particle has been measured,
yes.
Has been up, and the second particle has been measured too.
Yes. Okay. And mathematically, if you want to put it in this linear algebra formalism, this would be first basis vector, standard basis vector, tensor product, second basis vector. This would be a mathematical description that fits it. Yes. Other question?
So it's not possible to have two particles with both
It's possible, no, for sure. It's just not an interesting case if you want to study entanglement. But yeah, that's also possible. You could, so the question was if we could have 2 upspins here. No, that's definitely possible. You can also have 2 upspins. You can have all like linear algebra combinations for the product, tensor product space. So if you have E1 and E2 standard basis vectors for your first system and your second system, you can have E1, 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 E2, E2, E1, E2, E2. Everything's possible, like in formal maths. One thing we can do with this is we can look at a very famous example, which is Schrödinger's cat, which states or goes into a different direction I don't really want to touch too deep upon, but there the basic thought is that we're looking at 2 systems. Here we can look at the particle spin, and the second system is a cat, where we make the assumption that the cat has 2 states, it's either dead or alive. So with the formalism we have seen now, we can create separable and entangled states of this system. A separable state, for example, would be this here, where we have our particle in the up state and the cat alive, and the particle in the down state and the cat alive. So this is now not an entangled state. Why? Because we can neatly factorize it, as I said earlier. We can factor out the cat part and just have this description of the particle. So the particle and the cat have each description that is not dependent on the other thing. We can also do entangled states. This is the famous Schrödinger cat state, where we have the up state of a particle and the cat alive, or the down state of the particle and the dead cat. I think the original proposition was with like a poisonous atom, and if it's in the up state, then a poison vial breaks, and then the cat dies, in the down state. So yeah, we could have this superposition. And now what we can see here, this is an entangled state, and if we measure the spin, so if we check if it's up or down, we kind of kill the cat or don't kill it, because we project it in the state that is connected to the atomic state. So it means that by interfering with this, we kind of decide upon the fate of the cat. And this is this very fundamental and interesting concept of entanglement, where measuring one part decides upon the other part. Yes. So this is all the basics. Yes. With up, or what? With up and down, and also down and alive. No, you could have that. But so. Huh? But if it was possible to have upspin and alive and upspin and dead. Yeah, then if you have upspin alive and upspin dead, then you could factor out the upspin part, and the cat would be in a superposition of dead and alive at the same time. Yes, then knowing the state of the atom wouldn't tell you anything about the cat, because if you measure the spin up or down, you get the spin information, but the cat is still in its dead or alive state. So it's really what the entanglement means is that the information of what the other thing is connected to the first thing. So if you obtain information from one, you get information from the other one. So some states are just not possible to obtain? Are not possible to obtain. This would be upspin and alive is just like cut away. Upspin and alive is possible to obtain. Also, no, I mean, it's just that if you want to look at this entanglement, then this is not an entangled state. But there's also the state of having an upspin and an alive cat, or an upspin and having a dead cat. How do you know that you're in a certain state? This is by measuring like all the different parts of your system and getting an information out of it. So if you probe all your parts, you collapse your initial entangled state to something you know. So for example, if here you would measure the spin and you measure it up, then you know the cat is alive. And then you have the up cat alive state, and the other part vanishes. Yeah. Cool. So after we have been very pleased with quantum mechanics, we can go to the weird part of it, where we apply these these concepts and ask the big questions. The first big question that was asked by Einstein, Podolsky, and Rosen, wait, I need to check, just Rosen, okay, was the question for local realism. This is a very, very interesting thing to think about in like foundational physics. And what they were asking is if quantum mechanics adheres to local realism. So what is local realism? Local realism means that your system or theory you look at both obeys locality, which means that you don't have spooky actions at a distance. So not like how we learn that gravity first acts when we look at Newton's force laws, where we just have instantaneous force, but with some mediation. So what locality means is that if you are very far away from all the other things, they don't influence you. They need to kind of get close to you first to give you a handshake or, I don't know, cook you dinner. The second concept is realism, which means that a system exists and the state of a system exists without us looking at it, which is a very philosophical question. I think goes back to Platon, where we ask ourselves, if we don't look at the spin of our particle, does it have a spin, or do the spin starts existing when we measure it? And Einstein, Rosen, and Podolsky, and a lot of other physicists in early times said that quantum mechanics should adhere to local realism, which is the combination of these two, because else it would be very like unphysical, because everything we see does this. Special relativity and all the other concepts adhere to this principle. So they wrote a paper on it. Yeah.
What do you mean by local interaction?
Yeah. Yes.
But so you don't. I mean, how do you define that?
Yeah. The proper definition would be that information cannot propagate faster than the speed of light. So you're limited by the speed of light to reach something. So if I want to tell you something, then the maximum like speed I can tell you something is by the speed of light. If I do it faster, it would violate locality.
And the information could be anything.
Yeah. That is a light pulse, that can be a word sound, that can be the measurement of a quantum state, really anything you can tell another person that would in some way, I guess if you want to do it really foundational, change entropy of that thing would be exactly that. So locality means I cannot come to you faster than the speed of light. So they were really unsure about this, and they created a thought experiment, the Einstein-Podolsky-Rosen Paradox, which is famous, super famous, and which goes like this. If you have a system that creates such an entangled pair as we've looked at for the last 10 minutes, and you separate, so the entangled state would look like this, with, let's call the first one A and the second one B, just to make it more clear. And you separate these two particles really far, so far that they can't interact instantaneously because the light needs, 7 minutes to travel from one to the other one. And then you measure these two systems, these two particles individually at both ends. Then you can create a situation that violates local realism with quantum mechanics. So what we do is, we have our two particles, separate them. On the left one, we measure the Z spin. On the second one, we measure the X spin. Now, we have talked about Heisenberg uncertainty and know that these two things shouldn't be measurable at the same time with arbitrary precision. So we cannot measure these things from our system at the same time for one particle. So how does this work? How can we then create this paradox and measure these two things? What we do is we have these separated particles that are entangled and measure the Z spin on the A particle. This is the first one. What we then do by this measurement we've seen, we either get this state out or this one. So we either measure first one up or down. But because this is entangled, we also get the information of the second spin. So we now know if the B spin is down or up by just selecting the opposite of what we've measured for A. But now these things are still very far away. So if we now measure the x spin on B, which we haven't touched yet, we just have measured A, then we can obtain the x spin of B via measurement. And this cannot interact with A or anything because it's so far away. So we measure A, then we know the Z state of B because of the entanglement, but we can still measure the X state because it's so far away and cannot have interacted with the other particle because it's 7 light minutes away. So we create a very problematic situation where Heisenberg uncertainty doesn't seem to hold anymore. And if Heisenberg's uncertainty should hold, so we assume that quantum mechanics is correct, we have two possibilities. Either that these two spins are not part of the same physical reality, so there would be like a reality breaking and we cannot have both in existence at the same time, which already these three found to be not the case. So they focused on the other logical explanation, which would be that quantum mechanics is incomplete and something is wrong with quantum mechanics. And this is what Einstein, after 35, when this was released, focused on for the last 20 years of his life. He tried to find the addition to quantum mechanics that would make it complete. So now we've seen that with this thought experiment, local realism seems to be not possible for quantum mechanics. So what can we do about it and go the Einsteinian way? His idea would be that if quantum mechanics is incomplete, we need something to make it complete. What is the most foundational thing that we can add to a system to make it more complete? We can add more variables. So if we can't describe it with just position and momentum, we just add a bunch and see if at some point it makes sense. So this is what people try to do. This is called hidden variable theory. And what it means is that you just add more descriptors of your system that carry with your system and float around with it. So the particle with spin would now also have a color and a taste and, I don't know, a tone, a frequency, and whatever you can think of. And that this additional information that is carried with the particle would lead to the measurement being defined before we measure it. So recreate this local realism where everything is already present at one point. So the intuitive picture would be this, that you just have your spin, and now it's not only the spin, it has more information described by these variables. Yes. This was investigated for, I guess, more than 10 years after 35 by many different people. But eventually, there was Bell, who did a lot of research on it and first showed that you actually can create these hidden variable states without violating local realism. But then he, I think it's coincidence, I mean, I'm not an expert on the history, but proved the opposite, that you actually can't have it. So there's Bell's theorem, which says that quantum mechanics is complete with local hidden variable theories. So if you want quantum mechanics to be the right thing, then you cannot have these local hidden variable theories. What does local here mean? That means if I add infinite amounts of variables that are globally available by anyone instantaneously, then it still works. But if we want to have this locality, then it doesn't work in no way. Quantum mechanics is exclusive with local hidden variable theories. So if you look at our assumptions that we would like to keep locality and realism, then what Bell showed is that you can get to a mathematical inequality. And if you add quantum mechanics to this inequality, you violate it. And this is a very instructive proof that you can actually try to realize experimentally, which then doesn't test your assumptions of quantum mechanics. It doesn't test only your assumptions on locality realism, but it tests the assumptions you have on quantum mechanics. If you test this thing and it's violated, then that means that quantum mechanics, if you assume that quantum mechanics is right, but this is violated, then it violates your assumptions. So what you can say is, if I say quantum mechanics is right, and I find that this doesn't work, then one of these can't be true. So this is the actual scientific status we're on, is that if we think that quantum mechanics are true, then we cannot accept local realism. So either locality or realism is broken for quantum mechanics, which is kind of scary. And now we come to the Nobel laureates. Wow, that has been a journey. So what Clauser, with a bunch of other people now did, is he used this Bell's theorem to develop an experiment that you can actually test in the lab to see if this Bell's theorem is violated by nature. So he designed a performable experimental test. And how this test looks is very similar to the things we've seen until now. You have some entanglement generation, which creates our nice Bell pair, our entangled state. And then you separate these states, ideally very far, and then you can conduct measurements A and measurements 1 and 2 on each of the particles. So A1 means measurement 1 on particle 1, and A2 means measurement 2 on particle A, sorry. So measurement 1 on particle A, measurement 2 on particle A, and the same thing for B. And if you now, how you translate this to an experiment is, okay, so sorry, these things I've already said. So you want to perform the measurements on each side, and you want to have them far away so you can impose locality. And now what you really want to test is locality and realism. So you need some framework of measurement. So you need one more assumption, which is that you assume that you designed your measurements in a way that measuring A1 or 2 or B1 or 2 gives you either +1 or -1. So you measure a spin. This is not a restricting assumption. It just means that you kind of normalize your measurement results to some value, so it's not that complicated to look at. So if you have this, then you can write down this equation, which is the Clauser-Horn-Shimony-Holt inequality, or equality at this point. And this equation, if we look at it for 30 seconds, we can see why this must be true. So what you do is, these are the measurements A1. So this is the measurement of A1, this measurement of B2, B1, B2, A2, B1, B2. Now, if we look at these terms in the brackets, we can see if we measure B1 and B2, just arbitrary measurements, then these either must be equal or they're not equal. Seems to be a very trivial statement. But if they are equal, then this term gives plus or minus 2, but if they, and this term gives 0. But if they're not equal, then this term gives 1, and this term gives plus or minus 2. We don't know if it's plus or minus. But already from just measuring, we know that one of these terms must vanish. And then if you multiply this with the measurement of A, we know that this just switches the sign. So it doesn't matter what you measure either plus or minus 2. Now, if we assume local realism, which means that these are far away and can't talk to each other, and they exist at the same time, then we can just do averaging over this equality. We now did it for one time, we do it for 1,000 times, and just average the resulting value. Since this is always plus or minus 2, the average will be bounded by plus or minus 2. So what we do is we create the average of these terms, so we just multiply this out, statistically average it, and we get this CHSH inequality, which means that this should be an equal. Sorry. I think there's some constraint you can put on it to make this smaller, but the derivation here would just mean smaller equal. Yeah, so here on the right side, small equal 2. But we have this inequality. And this should hold, must hold for any system that adheres to local realism. And now we can come with our quantum mechanical system, measure this value, and see that it's larger than 2, and then we've shown that local realism can't be true. And this is what the Nobel laureates did. So this is the entire experiment. They developed all this theory, they came to this inequality, and now developed an experiment that you can, in the lab, prove that local realism for quantum mechanics can't be the right thing, if you assume the quantum mechanics is right. So yes, this is now obtainable in an experiment. Now, yes, that's where we can look at the 3 experiments that the people did. The one thing that we here should mention is that the actual experiments weren't carried out with particles with spin. They were carried out with photons, so light, with polarization. It's just an experimental detail, but if you wonder why there's not a particle spin everywhere, the math is exactly the same, but we don't look at an upspin or downspin anymore. We look at vertical polarization or horizontal polarization because we can easily measure that in the lab. And now we have all the tools to look at the free experiments. So we start with John Clauser, and he really did the fundamental work for it. First, he developed this inequality, and then he designed the first experimental setup. So what they did is they put a calcium atom in the center of an optical system, excited this calcium atom, and this calcium atom would, by chance, decay and create these entangled states that we've looked at. This is just a statistical thing that happens at some times, but if you measure for long enough, you can see these. So now you have these. So this is now not spins anymore. This is light with different polarization. So this means vertical polarization, horizontal polarization, horizontal, vertical. Now this light would travel in the contrary direction, and by implementing a polarization measurement, you can actually measure these spin states, which now are the polarization states. And this is like these polarizers that can measure this. This is the same technology, I mean, on the fundamental level which you have in your polarized sunglasses. So that is available. And he could prove that his experimental setup violates these CHSH inequalities. So, which is super, super crazy to think that this worked. But there were some questions to the experiment. First of all, if you want this relation to really be true, you need to ensure two things are very important: that these polarizers are so far away from each other that you can have them talking to each other. So you need to be like in a non-local condition where you can't have the measurement of this then influencing the measurement of this, because then that would work again. And this was not true for the case of Clauser. The second thing you want to worry about is you need to choose what you measure here. So if you create very favorable choices of the measurements you do, then you can actually create a situation where the inequality is not valid, even if local realism is true. This is because we do the statistical average and we assume that this is the true statistical average and no choice in it. So we need that this is truly random and that it's far away from each other. So what Alain Aspect did is he closed this locality loophole by changing the measurement setting during the time of flight of these photons. So you send the photon out and then you decide via a random generator which setting you measure. And this in like 20 nanoseconds, which is super fast. So very cool thing. So we had these switchable paths for the photons to decide what you measure. This closed the locality loophole. And they had a way better result at violating the inequalities. I think it's 5 standard deviations that they achieved. But the problem was the distance is still too small to have this non-locality criterion. So here comes Anton Zeilinger into play. And what he did is he first created a system that really has these strict local conditions. So you don't have these polarizers talking to each other. And he also closed the random number loophole with a super interesting idea. What they did is they made the decision of which state to measure here dependent on the light from distant stars. So they put the telescope at some star in the Milky Way, and then if they obtained one or the other signal, they decided to measure one or the other. And these are not the same stars, so different stars, like super many kilometers away, just to switch a polarizer in a lab. Super interesting. And then he also did major developments and contributions towards quantum information technology, which means how we can use this stuff for actually useful things. So I guess since we're already a bit over time, I want to show you two things. First, how these experimental realizations look, because I guess not all of you have been in an optics lab already. I got this picture not from Anton Zeilinger, but from Harald Weinfurter, which worked in his group for a long time. I mean, I got it from his website, not from him. But this is how such an optical setup typically would look. So you build up a bunch of like optical pieces, and you arrange them in a way that you have light going through them in a way that you want. And the cool thing about it is that it's super small, so you don't have a hadron collider. You can, I mean, this does a Bell state measurement, and it's like 1 by 1 meter, I guess, tops. I mean, you have the laser too, but 1 by 1 meter. And it's super modular, so you can do many modifications to it in short times. Yes. And this is what, I guess for the most part, what this year's Physics Nobel Prize was granted for, or gifted for, whatever verb to use there. And now I have over-prepared a bit. There would be 3 applications, how we can use them, but I think I want to focus on the conclusion first, and then maybe not even do the other things, so you can get to your lectures in time. But what I want you to take home from this is that first, quantum mechanics is non-intuitive and difficult, and that's okay. But exactly this weirdness leads to amazing phenomena that we haven't figured out still yet. There's still a lot of research that's done today on very fundamental quantum things, like how can these entangled states look? What crazy entanglements can we create? How could this be used for anything? The conclusion from the Nobel Prize measurements is that we might have to give up on local realism, or there's another way, we can also give up on free will. If we give up on free will and accept superdeterminism, then local realism is possible again, but I'm not sure which of both I'm more happy with. There are experimental tests to verify these super foundational quantum mechanics things, and there are many useful applications, which I couldn't show you. But the 3 things that got out of Anton Zeilinger's work was first secure key distribution, so quantum cryptography. You can send information from one place to the other without people being able to eavesdrop to hear what you say. This is one thing. Then it can improve measurements, which is not that, I find that interesting, but it's not super amazing. And the last thing is you can transport quantum states over a long distance by using this kind of entanglement. So this entanglement can store the information of one state, you can send it through outer space, come back to it, and still have the information encoded. Yes, so with this, there's just left to say thank you for being here and listening to my talk, and I'll be ready for further questions if you have any. That's it. Anyone?
I can ask something.
Yeah, sure. We don't have to.
First of all, I don't know any quantum mechanics, but I will ask my team.
That's completely fine.
The thing with Bell equality was that if we assume locality, reality, and truthfulness of quantum mechanics,
Yes.
Bell inequality is violated.
Yes.
Are there any assumptions we can weaken or strengthen in our quantum mechanics view that makes this wrong? So are there any weaker quantum mechanics that with these other assumptions satisfy the Bell inequality, or is it something very essential to quantum mechanics?
It's very essential. It's like the core principles. It relies on the measurement and the uncertainty of the obtainable quantities. So you really can't weaken it without losing quantum mechanics and putting a lot of results in question that we have found experimentally to be true. Yeah. Yes. Here in the last experiment, this one. Yeah. I think it's just some, the first experiment that proved it was just some meters. But I mean, if it's just some meters, you just need to be super fast. you have the light speed is your threshold. So if you can measure faster than the speed of light can propagate from one polarizer to the other one, you're safe. Yeah, so you really need to time everything super neatly. Now there's also been measurements of Bell states where you put the light on a satellite and reflect it there and go to a lab in China. So there has been this collaboration between Zeilinger and the lab in China where they do these Bell tests via 2 different labs via a satellite. There it's a bit easier. You don't have these strong time restrictions. But yeah, you just need to be fast. Yes?